Okay, welcome to AP Computer Science A. Welcome to today's lesson, everybody. Today is Thursday the 2nd, which means we are looking at recursion and binary search today. So my name is Rob Schultz. I teach at Bellbrook High School in Bellbrook, Ohio.
And I'm Jill Westerland. I teach at Hoover High School in Hoover, Alabama.
Oh, there we go.
Yes. Yeah. Can you hear me?
Yep, we gotcha.
Okay, good. Okay, so we're so happy that you're with us today. And here's where we are in Ohio and Alabama, respectively. And I think you're going to see where everybody else is that we have marked on our map. Is something happening?
There we go.
There we go. I don't know what's going on.
Yeah, I'm not sure.
I don't either. We'll make it work, though.
We'll roll with it.
That's right. That's right. Okay, so here's where our community is. We're so thankful that you're with us. And we're going to give out a shout out next, I think. There we go, to what we're doing today.
One.
Yeah,
okay.
Today we're doing binary search, and brand new yesterday was CS Principles release of videos. So I know that this is CSA, but they're our sister course, and many of you took Principles. You may have friends who are taking Principles now, and we want you to contact them and make sure that they're aware that as of yesterday, videos were released for CS Principles. There are two, the ones that I have check marked on yesterday's date. And then there are, 3, 6, 8 more coming. And you can see the dates on the left. And it's Mr. Bonarigo and Miss, I got her name covered up, I'm sorry, Miss Alano from Indiana. Mr. Bonarigo's from outside Chicago. And they will be covering with you, the CSP students, things about the Explore Performance task and the Create task. So if you happen to be taking both courses, be sure to watch those so that you know all the particulars and check in with your teachers. And if you have friends or siblings taking Principles, please let them know. All right, so last night we hope that you looked at Runestone or Practice It or Coding Bat and looked a little deeper into recursion. I've got a recursion compare and contrast for you to consider today. I did not include this one yesterday because the recursion on this particular algorithm is really not good. It can be done recursively, but it definitely is not what you want to do. You would want to do this particular algorithm iteratively. The recursion is a lot shorter, so originally you might think shorter, but I wanted you to look real quick at the functionality of the for loop on the iterative side. Does that look familiar to you? I'm going to assume you said yes, and I hope that you recognize that it is essentially a swap algorithm. If you've done a card program where you shuffled cards, you're doing that here. You're doing a little math with what's happening with N3, but it's a lot of a shuffle. You're moving around. N3 becomes N1 plus N2, N1 becomes N2, N2 becomes N3. So the next thing I have circled that I wanted you to notice is for the iterative algorithm, what's circled is how many times the loop is going to execute. So it's going to execute as many times as N, or the input. Now, if you're not familiar with Fibonacci, it's a numbering system that is where you add the previous letter with the previous two letters to form the next letter, and then you add the next two. I've got some code for you, and I've put some links in there so that you can read more about it. It's named for an Italian mathematician, so you should look that up. The recursive formula on the right, or algorithm, the base case is what I have circled in purple that it's going to look for. It's going to check for 1 or 2. But then if you notice, every time Fibo2 is called, it's going to call itself minus 1 and itself with the input minus 2. So I did a tree, and my example that you're going to see is that I'm going to put in 9. That means that when Fibo2 is called with 9, my result down there you can see is 34. But this recursive algorithm would end up making 109 calls. If you look back over at the iterative one, how many calls is that going to make? It's going to make as many calls as the input. So it's going to execute in a constant, as opposed to the iterative one, or the recursive one is going to fall under exponential. So I've given you the code in JDoodle. I'll also put it in the folder in a little while in source code. So play around with these two. If you don't know about Fibonacci numbers, please look them up because it's kind of interesting, and it's another math thing that you can add to your CS knowledge. There you go.
Okay, so just keep in mind that at the end of each review session, we're going to provide information and resources so that you can power up. And we also wanted to just, again, I know we do this every day, but I wanted to quickly review our approach and strategies to kind of get you prepped for today's lesson. So remember that we're keeping things course focused, concept based. We're trying to make sure we emphasize syntax and the importance of being able to handwrite code. And I know we've mentioned this a couple of times in the past, but if today is your first day joining us, Mrs. Westerland is doing a great job of modeling note-taking skills. And if you look out in the shared folder that we'll give you the link for later, you'll find her folder that has her notes that she's taking as we go. So make sure you're looking at her notes, but also make sure you're taking your own notes, because again, as you think about classes that are yet to come, that's a great skill to have. So, okay, so let's move on to today's lesson. Like I said, today we're looking at binary search, and specifically we're looking at the recursive approach. So if you think about prior knowledge, if you think about information that would be helpful to have kind of going into this lesson, we've already talked briefly about ArrayList and ArrayList implementation. If you aren't comfortable with ArrayLists, you might want to go back and rewatch those videos. It's also helpful if you have an idea of the iterative approach to linear search and binary search. So we're going to look at both of those as well. But I promise eventually we will get to the recursive approach to binary search, because that's really the kind of the main point of the lesson that we're looking at today. Okay, so for our 2-minute warm-up, here's what I would like you to do. I want you to complete the following method, and I'm going to move my little window here out of the way because something's blocking my paragraph, but complete the following method, search for num, that will take a sorted array list of integers called intlist and a target integer called target, and then return the index position of target if target is found in intlist. If by some chance the target value is not found in intlist, then your method should return -1. So feel free to use whichever approach you feel would be the most appropriate, or whichever approach you know. I know we've looked at traversing array lists, things like that. So see if you can come up with a little algorithm that will go through and find our target. And I'll give you about 1.5 to 2 minutes. So I'm not sure what happened there at the beginning. We had a little internet lag in there somewhere. That was strange. Hopefully everything, whatever it was, worked itself out.
Me too. Because it's not raining today. We can't blame it on that.
And while we've got a little time, I will say that I am wearing Hawaiian shirt number 4 because this is day 4 of Bellbrook's spring break.
I love it.
It's as close to spring break, I think, as I'm going to get this year, but. All right, about 1 more minute.
Tomorrow.
Yeah, I thought about that. A nice Panama hat and some sunglasses. And we had a Hawaiian themed party a while back, and I was hoping at the back of our pantry we still had some of those little umbrellas, the little, you know, and I was going to stick one in my coffee, but I couldn't find one. Okay, about 30 seconds to go, and then we'll look at this quick. Okay, let's take a look. I know I said you could use whatever approach you wanted, but I would be willing to bet that if we had a means of surveying the students that are following us right now, that you probably came up with something pretty similar to this. This is a very straightforward traversal of an array list. We basically start at index position 0. We continue as long as our loop control variable is less than the size of the array list. And if by some chance, as we're working through element by element by element, we find an element that is equal to our target, we return that position. Okay, this is probably the most straightforward searching algorithm, in my opinion, that there is. And this is actually called linear search. So linear search is really nothing more than just traversing an array or an array list and stopping when you find the value that you're looking for. Okay, we're going to go on from there, and we're going to talk about something that is a little more efficient. So, if I've got 20 or 50 or even into the hundreds of elements to search for, linear search with the computers we have today is fairly efficient. But imagine if we had thousands of elements or millions of elements to search for. Then we start noticing some lag time where things might be a little more time sensitive. So we want to start looking for searching algorithms that are going to be a little faster and work a little better to meet our needs. So we're going to break protocol a little bit. I know every lesson we've done up to this point has been PowerPoint driven with our little picture just up in the top corner, but I am actually going to pause our presentation. Let's see, can I do that? And I'm going to stop share so that we go full screen because I want you to see what we're about to do. I do this little demo, and I have to give a shout out to Jim Huggins at Kettering University because he's the one that I first saw do this little demo, and I thought it was so brilliant in its simplicity of how to demonstrate searching algorithms that I have done it every year with my students since. The problem is you need a phone book or a dictionary, and in this technical day and age, those are kind of hard to come by. So I do have a phone book, but it's at school in my room, and we aren't at school right now. So fortunately,
but I happen to have a dictionary.
Mrs. Westerland
That
had to have a dictionary.
It's not my best one ever.
And she was willing to sacrifice it for the
That's
cause.
Right.
So
That's right.
We're going to do a little comparison. So Mrs. Westerland, I would like you to look up the word recursion in your dictionary, but I would like you to do that using a linear search algorithm. Okay, so you're acting out a linear search algorithm. And for the students at home, I want to pay attention. I want to count how many comparisons it's going to take doing a linear search for Mrs. Westerland to come up with the word recursion. Okay, whenever you're ready.
Okay, so here's my dictionary. I'm going to move in a little closer. Maybe I can peek around the edge. And you can see that he wants me to look up the word recursion, but I'm going to start at the beginning, obviously, of our alphabet. And I want y'all to think, too, you do something all the time that is linear search. And if you're in my class and you're watching this, you might be screaming to the computer, I know what it is, I know what it is. What do you do if you're going to do homework and you know that one of the answers you need has something to do with the word Shakespeare? You're going to do Control F. Control F is linear search. It's searching that document for whatever it is you're looking for. So I need recursion. So I'm going to go all the way over here to the R's. I have to look straight away and find the R's here. REC. And this is like a dollar store dictionary. So it might not be that we have recursion in here.
Well, but so yeah. the point I wanted to make though was that if you're doing this as a linear search, you're going to start on page 1. So if you what's the very first word in the A's?
That's right. The first word in the A's.
Yeah. So I mean, you can go ahead and look and actually work through.
Yeah. Let's see what the first word in the A's is. God, these words are so tiny. It's actually the word A.
Okay. So if you were to start a linear search, could you read about the first 20 words for me?
All right. So we have A. We have Aaron's beard, aback, abacus, abaft, abandon, abandoned, abandonment, abase.
Okay, that's probably far enough. So imagine if we did a linear search, we were trying to find a word in the dictionary. If linear search was our only method to find a word, we would have to start at literally the letter A and read each individual word page by page by page until we come up with the word recursion. Okay, so let's try something a little different. What I'd like you to do is take the dictionary and open it to the middle.
All right, so y'all are looking at me. Here it is, basically the middle.
And tell me what word is in the upper left corner of the rightmost page.
Malevolence.
Malevolence. Okay, so what I'd like you to do, because recursion comes after malevolence in the dictionary, I'd like you to rip that dictionary right down the binding, rip it
All
in
right,
half.
so here we go. Here we go.
Okay, and then we can get rid of anything that
side
is in the half that does not include recursion. So with one comparison.
All right, y'all looking? So we have our two sides. This is the left side that we don't need, the A through M. All right.
So with one comparison, we've basically just cut our list in half. So now let's do the same thing. Take the piece that's left, open it to the halfway point.
All right, so everybody's looking. Here's the piece that's left.
Tell me what word is in the top left of the rightmost page.
All right, now we have the word site.
Site. Okay, so again, we're going to rip it right down the binding and get rid of the half that does not include recursion.
All right, so here we go. Ripping it again. All right, so now we have our two halves. And which side do we want to keep? Because this side starts with site, S-I-T-E. So where was our key word? It was in front of site, right? Q-R-S. So I need to keep this, but go ahead.
Okay, so yeah, so we're going to get rid of the half that does not include the R's.
All right, so we're getting rid of the S,
upper
I through X or Z, I guess.
So now with two comparisons, we have 1/4 of our list remaining. So let's do the same thing. Open it to the halfway point.
Okay. So now here we go.
And
I'm at postage.
Postage. Okay. So again, rip it right down the binding.
All right. So now I'm ripping. So this is the postage side, and over here is precursive through the S.
Okay, so now we're going to eliminate the half that does not include. And so hopefully by now everybody's kind of noticed that every time we do a comparison, instead of just eliminating the one value or the one word that we've looked at, we're eliminating half of whatever part of the list is left. So we went from an entire dictionary to half of a dictionary to a fourth of a dictionary. Now we have an eighth of a dictionary, or I believe actually we're at the point where we have a 16th of a dictionary. So we can probably stop at that point. I think that probably makes the point. But the idea is that every time we do a comparison, we're eliminating half of whatever part of the list is left instead of just one word that's in the list. Okay, and that's our binary search. So that's actually what we're going to be talking about for the rest of the day. Thank you for sacrificing your dictionary. I appreciate that.
You're so welcome. Anything for the CS calls.
All right, so let me see if I can get back to our presentation. There we go. There's our live demo slide again. Okay, so let's talk a little bit more about the mechanics of how binary search works. Let's see if I can get over there. There we go. So what I did was I put a list on the screen, a list of integers, even values that go from 0 up to 40. So we've got 21 even integers. The index position of the first one is going to be 0. The index position of the last one is going to be 20. And let's say for a second that our target that we're searching for is 24. Okay, so the idea with binary search is that when I call the binary search method, I'm going to give it the array list, I'm going to give it the target, but I'm also going to tell it what part of the list we really want to look at. We want to look at from position 0, index position 0, up to the last index position in our list, which is position 20. And then we're going to start working through this series of steps, similar to what Mrs. Westerland just did when she was working through her dictionary. The first thing we're going to do is we're going to calculate a middle value. And our middle is going to be the index position 0 plus the index position 20 divided by 2. So it would make sense that our middle position would be 10. And then because our target value 24 is greater than our middle value 20, just like ripping the dictionary in half, we can forget about all of the values that are less than or equal to our middle value. And because we can forget about all of those values, that really means that our low position is going to become one more than our middle position. We're now saying that we want to look at the values that are between index position 11 to index position 20. We're going to repeat that process. So step 2, we're going to recalculate our middle position as being 11 plus 20, which is 31. And remember that in Java, an int divided by an int gives us an int. So 31 divided by 2 in Java gives us 15. Our target value, 24, is less than our middle value, 30, which means we can forget about all the values that are greater than or equal to our middle value. And if we can forget about all of those, then really that means our new highest value, or the highest position we want to look at, is going to be 1 below our middle. So we're going to set high equal to mid minus 1. We still haven't found what we're looking for yet. So we're going to go back and we're going to repeat step 3, or repeat all of those as step 3. We're going to recalculate our middle value again. Our middle is calculated as 11 plus 14, which is 25. 25 divided by 2 gives us 12. And in this case, our target value is equal to our middle value. So at this point, we're just going to return our index position. We found the number we were looking for at position 20. I'm sorry, at position 12. So instead of taking 13 comparisons, as we would if we had done a linear search and compared to each one working our way up, it took us only 3 comparisons to find what we were looking for. And imagine that on a much larger scale, where we have thousands or hundreds of thousands or even millions of numbers to search through. Okay. Now, I want to ask a question. What would have happened if our target position had been 23 instead of 24? What would happen if we try and search for a number that turns out to be not in the list? So let's jump in the old Wayback Machine. We're going to go back about 45 seconds or so, and as if we were just coming to step 3. Okay, so we've already done step 1, we've done step 2, now we're ready for step 3, just like we did before. We're going to calculate middle as 11 plus 14, which is 25. 25 divided by 2 gives us 12. In this case, our target value, 23, is less than our middle value, 24, which means we can forget about all of the values that are greater than or equal to our middle value. And because we can forget about all of those, our high value is going to become 1 less than mid. So notice now our low variable and our high variable are both kind of referring us or pointing us back to, they're holding this same index position, 11. Okay, we're going to repeat our steps again. So step 4, our fourth comparison is we're going to say that mid is calculated as 11 plus 11, which is 22, divided by 2 gives us 11. So now everything's pretty much pointing at this one index position. Our target value 23 is greater than our middle value of 22, which means we can forget about everything that's less than or equal to our middle value. So as human beings looking at the list, we can see that we've grayed out all of the possibilities, but the algorithm doesn't know that. The algorithm is going to continue to do what we've told the algorithm to do. And in this case, because our target value is greater than our middle value, we're telling it that means that we can set low equal to mid plus 1. And we're going to keep going. We're going to try one more step, but now we've run into a problem because our low value and our high value have crossed each other, which means that we've missed the opportunity to find that value had it been there. So if we get to the point that our low value and our high values cross, then our target value is not in the list. That's our indicator that our target value isn't there, and we're just going to return -1 at that point. Okay, so that's the basic idea of how binary search works. Before we go in and look at a recursive solution, I want to show you the code for an iterative solution, just in case you've never seen it before. And I want to kind of look at this in relation to the 2 examples we've just done. We start out by making sure our low position is less than or equal to our high position. And as long as it is, we're going to calculate our middle. If our middle value is less than the target, then we increase our low position. If our middle value is greater than our target, then we decrease our high position. And we really only have 3 choices. If I'm comparing middle value to target, the middle value either has to be less than, greater than, or equal. That's really the only other choice. So if our low position is less than high position, the middle value is not less than the target, the middle value is not greater than the target, well, then the only remaining possibility is that the middle value equals the target, which means we just found what we were looking for and we can return our middle position. If by some chance we iterate through this loop, we keep going through the loop over and over and over again, we never actually hit a condition where our middle value is equal to the target, but we get to the point where our low position and high positions cross, then at that point we'll jump out of the while loop. We'll return location, which in this version of the code has a value of -1. Okay, so there's our iterative approach to binary search. Now, we've done a lot of different things, and the whole point of this was supposed to be a recursive approach to binary search. So let's jump into that. Let's take a look. Okay. What I would like you to do for the next, let's say 2 minutes, is I would like you to think about how we could implement binary search recursively. In other words, no loops. We only want recursive calls, but I want you to think specifically about 4 questions. What do we do if our low position is greater than our high position? What do we do if the middle value is less than the target? what do we do if the middle value is greater than the target? And what do we do if the middle value is equal to the target? Okay, so I'm going to give you about 30 seconds to kind of start maybe fleshing a little of this out on paper. And then I'm going to put a hint up on the screen to kind of help you out a little bit. Okay, so go ahead and go. We need more music.
We do. I'll have to go and look. I know a teacher turned some in.
Oh, okay.
I need to look for some.
Okay, here's your hint. I'm going to show you kind of the just basic skeleton structure of the code for the recursive approach to a binary search. But I still left those 4 questions in there. I left kind of the code that would answer those questions out. But take a look at what we've got. We have, instead of a while loop, we have an if statement. The if statement says if our low position is greater than the high position, well, then we have to respond by doing something. And otherwise, as long as our low position is less than or equal to the high position, which would make this a false statement, then this looks pretty similar to the code that was inside our loop in the iterative approach. We're still going to calculate a middle position. We still have to check and see if our middle value is less than the target or our middle value is greater than the target. So now you can kind of see where the answers to those questions would fit. I'll give you another 30 seconds or so, and then we'll start breaking those down one at a time and see how we would answer each of those questions. Okay, let's start working through these one at a time. So the first question we've got, what do we do if our low position is greater than our high position? In other words, we get to the point that we call our recursive binary search, and the low position and high position have crossed. Okay, well, if you think about what we did in our iterative approach, that was our signal that we didn't find what we were looking for. Okay, so really we're going to do the exact same thing. If we get to the point that we call our recursive binary search and we pass in a low value that has a greater value than our, a low position that has a greater value than our high position, then okay, that's going to be the signal that we have crossed paths. Our low and high values have crossed each other. We're just automatically going to return -1 at this point. If we pass in values for low position and high position that make this false, then we're going to jump down to the else. We're going to calculate our middle. So the next question is, as we start looking at our middle value, the value in int list that would be in that middle position, what do we do when the middle value is less than target? Well, this is where the recursion kind of comes back into play. We don't have anything that we're doing iteratively. We don't have any loops, but if you think about what we've done with our recursive binary search, we've basically called a method saying that we want to search in all of the values between low position and high position. So really all we have to do is say, okay, well now we want to call a new version of recursive binary search saying that we want to search only for the values between this low position and high position. So if you think about what we did in the iterative approach, we replaced low with mid position +1. Well, that's really the same thing we're doing in our recursive binary search. We're just basically calling the method again, but we're saying instead of passing low position back into this new call, we're going to treat mid position +1 as our new low position. So the first time we call it, we might have 20 elements. The second time we call it, we're only going to have 10 elements because we've just said to start our low position at mid position +1. Whatever value our call to recursive binary search returns to us, we're just going to go ahead and return back to the method that called us. Okay. And if our middle position happens to be greater than target, well, really, we're going to do kind of the same idea. It's just that this time, instead of substituting for our low position, we're going to substitute mid position -1 for our high position. Okay. So you can kind of picture as we work through this algorithm, I'm gonna call a version of recursive binary search that's going to give me 20 values to search, and then I'm going to add another one to the method stack that's going to give me 10 values, and I'm going to add another one to the method stack that's going to give me 5 values, and then 2 values and 1 value. So you can kind of picture the method stack as a stack of trays where we keep calling recursive binary search on top of each other, and then eventually we're going to get to the point where either low position is greater than high position, so we'll return -1, or we get to the point where our middle value is equal to the target, which means we found what we're looking for. So we can just return middle position. And at that point, middle position gets returned to the method below it, which will return it to the method below it, which returns it to the method below it. And all of those stacks of recursive binary search that we put on top of each other start popping off the stack. And at the end, we end up returning either -1 or our middle position because we found what we were looking for. Now, I know that's a lot to digest. We've talked about linear search, we've talked about an iterative approach to binary search, and we've talked about a recursive approach to binary search. The code for all 3 of those searching algorithms is out in the shared folder that we've made available to you. So my challenge to you tonight would be, first, go out and play with them a little bit. There is a main method where it'll generate a list of numbers. Modify that a little bit. Make it 1,000 values. Make it 100,000 values. I mean, play with it a little bit and see what happens as you run each of these different searching algorithms. But the other challenge I would give you would be actually see if you can modify this a little bit. So instead of an array list of integers, maybe it looks at an array list of dogs, or an array list of hippos, or an array list of animals. See if you can go through and search for your pet's name in a list of dogs or cats or hippos or animals. Okay. Let's see. Final question. I had one final question, and hopefully you've picked up on this. What has to be true about our data in order for binary search to work? There's one big difference between linear search and binary search, that linear search will work, but binary search won't if something is not true about our data. Okay. Well, the answer to that is, and the reason we specifically have to use a phone book or a dictionary for our live example, our data has to be in sorted order for binary search to work. So if you think about it, everything is based on a comparison of knowing whether our number comes before or after, or our word comes before or after, depending on what it is we're searching for. Well, if we just have an array list of random words that are not in order, or random numbers that are not in order, then there's really no way to know whether the number we're searching for comes before or after the number that we just found as our middle position. So in order for binary search to work, it's much more efficient in most cases than linear search, but the catch is our data has to be in sorted order. If our data is not in sorted order, then we really don't have a lot of choices at this stage. We would have to look at linear search instead. So here's our debrief and summary for the day. Okay. Binary search can be implemented iteratively or recursively. There's an iterative implementation and a recursive implementation to binary search. Binary search essentially works by eliminating half of the list with each comparison, as opposed to linear search, which only eliminates the one number that we just compared to. And this, in most cases, makes it much more efficient than linear search. So every once in a while I'll have a student say, well, give me an example of where linear search is more efficient than binary search. Well, imagine we've got 1 million integers that we need to search, and the number that we happen to be looking for is in slot 0. Well, if I'm doing binary search, I have to go to the middle, and then go to the middle, and then go to the middle, versus linear search, because I'm fortunate enough to have that number that I'm looking for in that first position, linear search would win in that case. So I can't say 100% of the time that binary search is always going to beat linear search. A lot of it kind of depends on the data and what it is we're searching for. And then the last little bullet point here for our debrief and summary: binary search will only work when data is in sorted order. That's our lesson for today. So here's the idea for our power up. Okay, make sure you take a look at bit.ly/CSA_exam review 2020. And again, remember that the bit.ly links are case sensitive. Out there, you'll find you'll find the folder that has Mrs. Westerlund's notes, and you'll find all of the folders and files that we've shared for past lessons, as well as a folder for today's lesson that has today's power up and then examples of code. So for today's power up, take a look at the lesson resources from the CED. Again, there are some Runestone examples, Practice It, and Coding Bat. Tomorrow, I'll start our power up with just a quick example of something you might see in Coding Bat. But like I said, the main goal for tonight's Power Up, actually see if you can implement a binary search with an array list that you created based on Monday and Tuesday's lessons. See if you can go back and create an array list that will, or see if you can create a binary search that will let you search an array list of dogs or cats or horses or hippos or animals or whatever you may have put together. One last thing, and then I'm going to turn it back over to Mrs. Westerlin. Tomorrow, we're going to be looking at sorting algorithms. So if you have some time this evening, there are some great resources that are available on YouTube to watch that involve sorting. Tomorrow, we're going to watch just a small segment of, I'll move my window out of the way here again. We're going to watch a small—
Rules of Modern Living.
Yes, thank you. My window was in the way.
It's wonderful, but wait till tomorrow and then watch.
Yeah, hold off on that one till tomorrow. We're going to watch a small segment of that one. But if you get a chance, just for fun, take a look maybe at one of these others that shows a visualization of some of the sorting algorithms that we might talk about tomorrow. Okay.
Yeah.
And then I do have one more slide I wanted to throw in, and I just found this in some notes when I was looking through some recursive stuff. I thought this was kind of funny, so I thought I would add this in. If you know anything about recursion, you know not to order the combo platter.
Oh, wow.
one of my students shared that with me, and so I thought I would throw that in. Okay.
Unless you're really hungry. Y'all may be really hungry right now wherever you are, and you wish you had a combo platter.
That does sound really good, but a combo platter that contains a combo platter, which would contain a combo platter, which would contain a combo platter.
That's funny.
Yeah.
That's really good. Very good. And I was going to throw in too, and you all probably know this because you're teenagers and y'all are 5 steps ahead on this kind of thing, but GitHub that we love and sometimes don't love, but mostly we love it. All of the answers to Coding Bat are on GitHub, thanks to whomever put them there. So if you're working on Coding Bat and you begin to get really frustrated and aggravated, you can, go out and get a hint for yourself from GitHub. The other thing is sometimes my students have an easier time and less frustration with the Coding Bat ones as they get harder and harder if they move the code to an editor and work with it there as opposed to staying in Coding Bat. I mean, you may have no trouble, but sometimes you run across one that you just are missing the forest for the trees. You can't see it. So that's just, helpful hints from Jill today. Okay, so I love these cute little dogs of Miss Kemp's. I don't remember all their names. They're all 3 Pacific Islander names. I don't remember them, but I just summarized them as a crew. And I think my next dog, whenever Bo needs a buddy, is going to have to be a long-haired dachshund. They're so cute. And the snow in Reno, and I love this cat peeking over at us from Salt Lake. And Emily sent a rhyme. And Emily is an 8th grader who I don't even know is taking CSA. She's just watching these with us because she wants to learn Java. So shout out to Emily in California.
Oh, that's really cool. Welcome,
isn't that
Emily.
Cool? She wrote a little note about that. She's in the 8th grade and she just wanted to participate. So
good for you. Welcome aboard, kiddo.
So that was cool. And Ryan's cute dog that he's playing chess with. I mean, we might get that bored being at home with our family that we begin to play chess with the dog. I don't know. I don't think Bo would do very well at chess. That's funny. And send us your input. You can make us a note. You can send us information. You can send us a picture, a song, anything. It's fun to see where y'all are from and what's happening. And another shout out for CS Principals. Let your friends and buddies know that they have got videos specifically for them, Mr. Bonarigo and Miss Alano. And I think that's it for today. So
I think we're at the end.
cb.org/tech if you have a tech issue. And thank you for being with us. And I don't know, we hit it. Kind of bell to bell again.
Yeah. Thank you all for watching. And again, have fun playing with binary search tonight, and we'll see you tomorrow.
Yeah. Same time, same place.